So yesterday we have started a new chapter on the calculation of the inverse of a matrix, and we have seen that this might be helpful in a lot of applications. So to summarize, the matrix inverse can be very helpful first in knowing if we change one of the parameters of the force vector, what will be the effect on the displacement in any displacement. So here you have x1, x2, x3, x4, x5, x6. So if you are interested, for example, to know if I just change f4, what will be the effect on just x1? I don't care for the other displacements. How can I do this in a fast way? Because if I want to do the conventional way, I should each time I vary f4, I should perform Gauss or LU factorization to determine what will be the effect on x1, and this will be coupled to the effect on other displacements x2, x3 until x6. Now we will develop a method that will help us into directly assessing what will happen to x1 if we change f4. And in this method, we will use the inverse of the matrix. This is why it's very important to know how to calculate the inverse of a matrix. Last time we have seen that first, as a first step, okay, we can find the inverse of matrix by several methods. The first one is to start from the definition, because from definition a minus 1 times a is equal to the identity matrix. And then starting from this definition, if we just do the multiplication of a times the terms of a minus 1, we will end up with the following result. And we have seen yesterday, and this result will lead to 9 equations, 9 unknowns, by just setting, for example, this term is equal to 1, this term is equal to 0. So if I change the form into a matrix form, I will end up with a system of 9 equations with 9 unknowns. So matrix A here, matrix A will be a 9 by 9 matrix, which is really hard to if I want to solve the system by Gauss elimination, it will need a lot of time. We said that here Gauss is better than LU because already I just have here one vector. Okay, so here I have just one vector, so I'm not changing it. This is why here is Gauss elimination is better than LU factorization, since I don't need to change my vector here. I will not change it. I will just operate once. Okay, but the problem is, even with that I am operating once, my matrix is so large. So now imagine if you have a 5 by 5 a system of my starting matrix. Okay, my starting system is 5 equations. Okay, so if I have my matrix will be 5 by 5, and in this case, if my matrix is 5 by 5, I will end up with 25 equations. Okay, so if I'm solving initially for a times x, so I have a matrix A times x. So let's say x is just 5 unknowns, but I want to solve for a minus 1. So a minus 1, to solve for it, I will require to do 5 times 5, which is 25 unknowns to solve for. So Gauss will take a lot of time. This is why we say here that we need to come up with a simpler method to calculate a minus 1. And this simple method that we can come with is by going back to the definition of how to get a minus 1. So if you remember, the first column of the identity matrix is obtained by doing the multiplication of this matrix of coefficients times the first column of a minus 1. So you can write, because how you obtain 1 here, you just do a11 b11 plus a12 b21 plus a13 b31. You get 1. Then you multiply the second row by this same column, you get 0. And you multiply the third row by the same column, you obtain 0. So you can now, instead of having a one matrix 9 by 9, you can divide this process into 3 steps. So I will write to get first v11, v21, v31. I just use this step. Next step, to get the second column, I write that matrix A times the second column of a minus 1 will give me the second column of the identity matrix, which is 0, 1, 0. And in the final step, I will take the matrix of coefficients A times the third column of A minus 1, which will give me the third column of the identity matrix. So now, instead of solving for 9 equations, 9 unknowns, okay, so I don't have any more a matrix 9 by 9. I reduce the computation to a matrix 3 by 3. But I should repeat this procedure 3 times. But even if I repeat it 3 times, it will take less time than doing a 9 by 9, than solving a minus 1 for a 9 by 9 matrix. Okay, and we will see how. So here, if you look well at your system, the advantage is that matrix A is not changing. What is just changing is this factor. So you recall which method we use in this case? Which method we use in case A is remaining the same, just I am changing the B factor? Yes, very good, Hassan. We use the LU factorization. Okay, so now let us perform, all we have to do is to perform LU factorization to get a lower and upper matrix. And once we get the matrices, now to solve for V11, V21, V31, we do forward and backward substitution. Then we will repeat this for V12, V22, V32, and then for V13, V23, V33. So we find A minus 1. We will do an example in detail together. In this example, we will review in this way how to do LU factorization. And we will then see how we can get, using LU factorization, how we can calculate the inverse of a matrix.
دكتور
Yes.
هلا هيدا يعني كل واحدة منهم شيء 3 equations and 3 unknowns.
بلى مظبوط.
هيدي ما بتنحط على الكالكوليتر انه المفكك.
هلا هي بتنحل على الكالكوليتر، بس انا اذا بعطيك 4 باي 4 مثلا.
عم بحكي هيدي انه هيك.
Yes, this one yes. بس انت لو اعطيتك هيك سيستم، اذا بتحط لي بتعمله على الكالكوليتر وبتحط لي الجواب، ما بحسب لك العلامه. يعني انا I should know that you understood the method. You can verify على الكالكوليتر.
ايه اكيد.
Yeah, you can verify of course. حتى يعني verification step can be done. بس the idea is to know how to do the method. يعني أنا ما بيهمني الجواب، بيهمني التكنيك to get the final answers. This is why I told you بالexam, please put all details, not just the answer. If you just give me the answer, it's a bad sign. Okay? So, for example here, if you just compare how to get I minus 1, if you compare the two methods, which are using Gauss elimination or computing or using LU factorization to get A minus 1, we can see that higher is the number, higher is the dimension of my matrix A, then the number of operation will be much higher with Gauss. So you can see that the difference is largely increasing as n is increased. And so it is increasing very fast. The number of operation is increasing very fast in Gauss compared to LU. This is why we say that LU factorization is much more convenient to calculate A minus 1. And since here we will benefit from the advantage that A is not changing, so just B is changing. Okay? We will practice together this on the following example. And just before doing the practice, we will see what is the importance of using the matrix inverse. So now we had introduced the method to find the inverse of the matrix, but why it's helpful to find A minus 1. So for example here, if you consider your initial system is matrix A times X equals to B, okay? Now, if you multiply both sides of your equation by A minus 1, what do you get? First, for the first side, you get A minus 1 times A times X equals to A minus 1 times B. Now, A minus 1 times A is the identity matrix. So you end up with vector X is equal to A minus 1 times vector B. And therefore, if you consider now what will happen, now you will come up with a decoupled solution for x1, x2, x3. What do I mean by decoupled solution? Before, when we solved for x1, x2, x3, we had 3 equations that are coupled. Now, of course, when we did first the Gauss elimination, the coupling between equations was a little bit easier because you can solve by backward substitution. Okay, but in all cases, still you have coupling between the equations. So let's say if you are doing backward substitution, if you want to get x1, you will start by x3, then move to x1. But what if I just want to find x1 without calculating x2 and x3? This is possible by using the matrix inverse A minus 1. So now, once you calculate A minus 1, you can say that vector x is equal to A minus 1 times B. And now what will be your equations? X, for example, if you just want to get x2, you don't care for others, for other variables. So you have x2 equals to v21 times v1 plus v22 times v2 plus v23 times v3. And now, so this is called a decoupled solution. I can get any of my displacement variable without knowing the others. Okay, and this is very helpful if I want to conduct a sensitivity analysis. What do we mean by sensitivity analysis? So let's say if I just varied B2 and I want to see the impact on X2, I can do it in a very simple way by just replacing B2 by its value. And for example, let's say I know that for example B1 okay is 1, B2 is 100, and B3 is 0.1, for example. So it's very clear that the major effect on X2 will be for this term. Okay, of course, if we consider, I am considering that V21 and V23 are not, let's say, very large. Okay, so if I just vary here, B2 will have the dominant effect on X2. So let's say if I double B2, okay, I can expect if B1 and B3 are very small compared to B2, and V21 and V23 are in the same order of V22, then X2 will nearly double when I double B2. Okay, so I can have an idea about the effect of my coefficients B1, B2, B3 on X2 in a simple way. And in case B1, B2, B3, let's say, are close to each other, not very far from each other, all I have to do is just to do numerical replacement, and I can get the effect on X2. Okay. So in this way, whatever I vary here, I can directly see the effect on X2 without having to repeat the solving operation from zero. Okay. So this is the advantage of using the matrix inverse to do a sensitive analysis on the effect of any element of the forcing vector on my solution. So as you can see here, you can find by using the inverse of matrix, you can get a decoupled solution for x1, x2, x3 that you can find independently of each other. So whatever is the displacement you are interested in, you can directly get it without having to calculate other displacements. So this is the first advantage of using the inverse of a matrix. Now, together, okay, we will do together an exercise. We will compute the inverse of the following matrix. Okay. So the idea is to get the inverse, as we said, the first step will be to use the LU factorization technique. Okay. So now I want to solve for A minus 1. So I want to solve for V11, V21, V31, V12, V13, V22, V23, and V32, V33. Okay? As we said, in order to simplify the analysis, in order to not get 9 equations, 9 unknowns, okay, then we should use the LU factorization. So in a the first step to do, okay, will be to say that A, matrix A, times the first column of A minus 1, which is V11, V21, V31, equals to the first column of the result. And when you do A times V, you expect to get the first column of the identity matrix. The identity matrix is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, so now you expect to get this first column. When you do A times the first column of A minus 1, you will get 1, 0, 0. Okay, now in order to solve for this first vector, we will use the LU factorization process. Okay, so the first step will be to decompose A into the product of a lower triangular matrix L times an upper triangular matrix U. And how we can come up with L and U? We have seen two techniques together. First, the LU factorization and the Cholesky method. Okay. Now, to be able to use Cholesky method, we should verify that if my matrix is symmetric and is positive definite. Here, it's not the case, because if you look at the diagonal here, you have it's not a mirror. So 1 is different than minus 1. So we cannot use this method. So we should use LU factorization. Okay. So let us use LU factorization. To fill L and U, the technique is to perform Gauss elimination for the following matrix. And as we proceed, we replace the factors of elimination in L. So L will be of the following form. Matrix L will be of the form. As we said, it's a lower triangular matrix. And for this case, we have ones in على diagonals. مش كل اللور triangular matrix بيكون عندهم 1 على diagonal. بس نحن بهيدي الميثود of LU اوكي بيكون في عندي 1 على diagonal و zeros in the upper part. Now the other factors will be, if you recall from Gauss elimination, when we do Gauss elimination, we will calculate factors F21, F31, and F32. Okay, so now when we proceed with Gauss elimination, we can fill the lower matrix, and we will come up with the upper resulting matrix. So now this is the first step we will do. Let us do it together. So we start with this matrix A. The first step, I consider the first equation as my pivot equation, and I verify that my pivot element is the highest between all elements in the same column below it. So the elements below 2 are 1 and 0. Both are smaller than 2. So this is my pivot equation. I don't need to do any pivoting, and I can start. Now I can start to define my factors. I have that F21 is equal to 1 over 2 equals to 0.5. And my second factor is F31 equals to 0 over 2, which is 0. So now already I can say that I can update my L matrix. My L matrix now is 1, 0.5, 0, and 0, 1. I still have just one element to find to be done, this one, and 0, 0, 1. Now concerning U, I will update my U. To update U, I will now change these coefficients accordingly, and these ones. Okay, so now to start with, I have the first equation will remain as it is. This is the pivot equation. It will remain unchanged. 2 minus 1, 0. Now, in the first step, of forward elimination, I use F21 to eliminate this element. So I expect when using F21 equal to 0.5, this element will become 0. I can verify this. It's very simple to verify. I do 1 minus F21, which is 0.5, times the element in the pivot equation in the same column of 1, which is 2. So 1 minus 0.5 times 2, I verify that this is equal to 0. Now, I proceed for this element. This element now will be replaced by 2 minus F21, which is 0.5, times the element in the pivot equation in the same column of 2, which is minus 1. So minus 0.5 times minus 1, it's 2.5. So now I can update this coefficient in my upper triangular matrix. This is 2.5. Now, the third step, I will replace here. I have 3. Here, you can directly, when you see 0 in the pivot equation, so this element will remain unchanged. And this rule, you can directly use it. Why? Because you will do 3 minus factor F21 times 0. Since the factor is multiplied by 0, so the element will not change. So when you see a 0 in the pivot equation, you can directly say, then I will no need to proceed. I will stop. This element will remain as it is. And so you can put here directly C. Now you are done with these coefficients update. Now you will move to the second step. You will do the forward elimination now for this term. What is nice here is that it is already 0. So when already you have 0, also you can say directly no, nothing will change here. And even if you apply a rule, F31 is 0. So you will get the same elements as they are. So you have here 0, 1, and 4. And now you are done with the first step. Now, since you updated these coefficients, and now you have zeros in the first column below the first element, then now this row is locked. We say that this row is locked, so I cannot anymore use it as pivot equation. Now I should change my pivot equation. Okay, my updated pivot equation will be this one. And of course, but I should work, I should not erase because I will need it, okay? So now, this is my updated matrix. I will now move to the second equation to be my pivot equation. Okay, and now I will proceed with the forward elimination. I want now to eliminate this term here. I want to have 0 here, okay? So now I should define factor F32. Let me check questions. Yes, we will find F32 now, exactly. So now to find F32, we will say that F32 is equal to 1 over 2.5, which is equal to 0.4. Okay, so now I can update here in L, in my L matrix. This term is known now. It's equal to 0.4. It's not anymore unknown. So L is done. I am done with matrix L. It's completely known. And then I will move to complete LU. So now I just still have to update this coefficient 4. So I will replace 4 by 4 minus. My factor F32 is 0.4. Just here, okay, so it's 0.4 times what? I should multiply 0.4 by 3, okay? So it's 4 minus 0.4 times 3 is equal to 2.8, okay? So now I updated my the coefficient here, and now the final step, okay, will be now to to start with my, if you want to get my vector v11, v12, v21, v31. Okay, so here now let us see the final expressions of my matrices. Okay, so now I can, let us go to, so here we already did this exercise with the previous session. I will just repeat for you. If you want the method. Okay, just here what we do, and we will do together another. We will continue the example we started with the other section. So here, these are the matrices I obtained. Okay, the upper matrix is 2, -1, 0, 0, 2.53, 0, 0, 2.8. We have seen how we got this matrix, and for the lower matrix is 1, 0, 5, 0, 0, 1, 0.4, and 0, 0, 1. Now, what is the first step to do? The first step to do is to find the vector v11, v21, v31. Okay, so which constitutes the first column of A minus 1. So the technique will be to say that matrix A times V will give me the first column of the identity matrix, which is 1, 0, 0. Okay, now we will proceed with the LU factorization. The LU factorization consists of the following. Once I have LU, I will replace matrix A by L times U. Okay, and then I will say that L times U times V is equal to vector B. And now I will do the solution in 2 steps. The first step will be forward substitution. What do I mean by it? First, I set U times V is equal to vector D. Okay, and then I will solve now. I will check what is D. To solve for D, I write L times D equals to B. So if we apply it here, the matrix L is 1, 0, 0, 0, 0.510, 0, 0.41 times D, which is unknown, and I want to find it. So I just replace it by a column vector D1, D2, D3 with 3 unknowns, equals to my vector B. In the first step of LU factorization, my vector B is vector 1, 0, 0. Okay, now to solve for D1, D2, D3, all I have to do is to do the forward substitution. Why we call it forward? Because I will start to solve by the first equation, because the first equation will directly give me D1, since these coefficients are 0, because I'm dealing with the lower triangular matrix, so I have zeros here. So now if I do the expansion, I have, for the first equation, I get 1 times D1 minus 0 times D2 plus 0 times D2 plus 0 times D3 equals to 1. So the first equation will give me that D1 is equal to 1. Now I continue, I proceed. Now to get D2, I move to the second equation. Okay, in the second equation, I have 0.510. I will multiply them by D1, D2, D3. So I get 0.5 D1 plus 1 times D2 plus 0 times D3 equals to 0. And now what is good is that already I calculated D1 in the first step. So now this is the forward substitution. I replace it in my equation and I get then the value of D2. Now, the third step, I move to row 3. In row 3, I get 0 times D1 plus 0.4 times D2 plus 1 times D3 equals to 0. And since already I calculated D1 and D2, I replace them in this equation to get the value of D3. In this way, I will find what are D1, D2, D3. Okay? Once I get vector D1, D2, D3, now I will move to the next step. The next step is to do the backward substitution. Okay? In backward substitution, now I will get my desired vector, which is V11, V21, V31. By going back to the definition of D, what was D? D is the upper matrix times vector B. Okay, so now since I got what is vector D, I got D1, D2, D3. Now I write that the upper matrix times V1 vector V is equal to vector D. So now I put vector D in its place here, and now I will move in the opposite way. I do backward substitution. Why? Because now I'm dealing with an upper triangular matrix, so zeros will be in the lower half. So now it's better for me to start from here, because if I start from the third equation, I get that 0v11 plus 0v21 plus 2.8 v31 equals to 1. Equals to 0.2, because now I'm solving with the third equation. So now when I got this, I can get v31, which is 0.2 over 2.8. I will now continue. I will proceed now to the second equation. So if I proceed to the second equation, I get 0.0 times v11 plus 2.5 times v21 plus 3 times v31 equals to the second element here, which of D, which is minus 0.5. So I can get now v21. And finally, I move to the first equation. So for the first equation, I have 2v11 minus v21 plus 0v